The last ideas in Chapter 2 involve problem solving, quantitative problem solving with all the kinematic variables. And the nice thing about it is that there are only 3 equations that you ever need to use. Here they are. That in all of these equations, the F subscript means the value of some variable like final velocity. In this case, the value at the end of some time interval, and during that time interval there was constant acceleration. And then V initial would be the value of that variable, like initial velocity in this case, at the beginning of the time interval when this constant acceleration was happening. Those are the only 3 equations you ever need to use, and really the only trick, sometimes it's complicated, sometimes it's not, is to figure out which is the best one, the easiest one to use. So let's look at an example of a problem. Imagine a plane on a runway, and in order to take off, it has to get up to a speed of 40 meters per second. So it has to get up to a speed of 40 meters per second, and in order to get up to that speed, it's able to accelerate at 6 meters per second per second. That is, if it starts from rest and starts accelerating, after 1 second its speed will be 6 meters per second, after 2 seconds its speed will be 12 meters per second, and so forth. What we'd like to know is how long the runway has to be in order to ensure that the plane can go far enough along that runway to get up to the 40 meters per second. So when you're approaching a problem like that, you know some kinematic variables and you have to calculate some other kinematic variables. Nice place to start is not with the calculation, but by getting a clearer picture of the situation. It's good to get into this habit starting early, because when situations get more complicated, having this habit will be very, very useful, very helpful. So first, get a good idea, get a much clearer idea of what's going on here. One way to do that is with some kind of a diagram, like a motion diagram to show what's happening. We imagine the plane starts here and then picks up speed, and then at the end of the 5th time interval, that's the time when it takes off. That's the moment when its speed has gotten up to 40 meters per second. So you need a runway that's at least long enough to get the plane allow the plane to speed up all the way from 0 speed up to 40 meters per second. So the plane will have 0 speed at this point. And once we have a diagram like that, it's good to do a couple other things. First, be clear about what the coordinate system is, which way is positive and which way is negative. That becomes important very soon, and if you don't get into that habit, you will make mistakes. And also decide, speaking of coordinate system, decide where the reference point, where the origin of that coordinate system will be. And usually we put the origin of the coordinate system, x equals 0, we put it at the point where the interesting behavior, that the accelerated motion, starts. So if the plane is starting from rest and starting right here, this is 0, the origin of the coordinate system, and it's xi, the location at the moment when the accelerated motion started. All right, that's an important part of understanding what's happening in the problem. Another part is just listing everything you know and everything you don't know. That seems kind of simplistic. It might seem kind of simplistic in some of these examples, but It becomes very, very useful later on when you have more complicated problems. In these situations, in kinematic calculations, there are only 6 variables you ever have to worry about. The initial and final location, right, the point where the accelerated motion starts and the point where the accelerated motion ends, the initial and final velocities, velocity when the accelerating started and the velocity when the accelerating ended, and then acceleration, and then the length of time spent doing that accelerated motion. So we know this because we set up the coordinate system that way. We put the initial location, the point where the accelerated motion starts, right at the origin of our coordinate system. And then the final location is this point right here. And that's really what we're trying to calculate. The total distance from here to here, the total distance from xi to xf, that's how long the runway has to be to make sure the plane can take off. And here's the speed that the plane has to have when it's here at xf. And there's how fast it accelerates, and we don't know how much time it takes to get from one end to the other end of the runway. So this is what we're trying to find. So obviously we need an equation that has x final in it. And there are 2 possibilities, that this equation has x final in it, and this equation has x final in it, but this equation also has delta t. And we don't know anything about delta t. We could figure out what delta t is, but it's easier and quicker just to skip that step. So what we really need is an equation that has the variable we're trying to find and an equation in which our goal, is the only unknown quantity. So that would be this one. We know every other quantity in this equation except xf. So at this point we just put in all the numbers that we know and then do the algebra to solve for xf, and let's see what we get. So the final velocity, 40 meters per second, squared equals initial velocity of 0, squaring the initial velocity, plus 2 times the acceleration, which is 6 meters per second, times x final, that's what we're trying to solve for, minus x initial, which is just 0. So let's work through this a little bit. 40 times 40 is 1600. Meters per second times meters per second. And we have to treat those unit labels as if they were algebraic variables, so we end up with meters squared over seconds squared equals this, 2 times 6 is 12 meters per second times x final. So x final will just be 1600 divided by 12. Or to be more specific, 1600 meters squared over seconds squared divided by 12 meters per seconds squared. And that comes out to 133. And the 1 over second squared in the numerator is canceled by the 1 over second squared in the denominator. And one of these 2 meters is canceled by this meters, so the only unit label that we're left is just plain meters, that's exactly what we're looking for.